Good afternoon, organic chemistry students. I want to give you a real brief overview of some things and talk about a few concepts that we haven't covered yet. So, real quick reminder, today is the 18th. We did not have class again today. Hopefully we'll have class on Friday, the 20th. I'll let you know via email still about lab once I know what the university schedule will be like for tomorrow on the 19th. If we're in class, likely we'll have some at least shortened lab period if whatever. So please pay attention to your email. Remember, problem set number 6 is due later this week. Right now it's still tentatively due for Friday night, but we'll play it by ear in terms of the time. So now let's look at an example as we consider reactions with substituted benzenes. So problem 18.16 in my book, second edition, I have at home, asks you to draw products formed when each of these reactants is treated with nitric acid and sulfuric acid, so a nitration reaction, and state whether the reaction occurs faster or slower than benzene. So let's real quickly go through these options here. A is acetophenone, where we have a C double bond O CH3, a ketone group there. B is benzonitrile with the cyano group. C is phenol with the hydroxy group. D is chlorobenzene. And E is ethylbenzene. So I'll pause for a moment. Alright, now, so let's look at these. So I went through these. In A, we notice that we've got a meta-director that's also a deactivator, as all our meta-directors are deactivators. Why is this a meta-director? The carbonyl carbon, remember, contains partial positive charge. So that's deactivating if you draw the resonance structures for that, or for the ionic intermediate. We should predict this to be slower and a meta-director preferred. So I've drawn here with the nitro group meta to the carbonyl group, and it's slower. Similarly, in B, the cyano group has a partial positive charge on the carbon and is slower in a meta-director. If you look at C, the hydroxy group is very activating, and so depending on what temperature we run this reaction, if we run it at low temperature, we should be able to limit it to ortho and para substituted, monosubstituted products shown over here on the right side there. But if we run it at high temperature or with large amounts of the nitric acid, we could go to the trinitro compound, which is known as picric acid and is quite explosive. So we wouldn't want to do that in lab. We want to be very careful about how we do that reaction. In D, we have a chloro group, which is deactivating, but is an ortho-para director. So halogens, halobenzenes, chloro, bromo, fluoro, or iodobenzenes, right, are deactivating but ortho-para directors. So they're going to occur slower. Nitration is pretty much going to stop at monosubstituted. In choice E, we've got ethylbenzene, which is a R group, an alkyl group. It's mildly activating and an ortho-para director, so we should expect a mixture of the ortho and para products there. And if we think about from steric standpoint, the para would be preferred, so probably a little bit more of that. So here is a good example. If we look at these, one thing we want to consider is that in the first two cases there with the orange, they're slower and they're deactivating, and once we get there, it's going to be hard to do another substitution reaction without forcing conditions. In the case of the C, it's deactivated compared to phenol, so it'll be slower to do another reaction. And same thing with E. Okay, nitration, nitro groups are deactivating. However, if we look ahead in the chapter at some of the reductions of nitro groups, which we'll talk about hopefully on Friday, if not sooner, those reductions make into a amino group, and aniline derivatives are activating. So we'll pause.